Beneath the calm turquoise waters off the western coast of the Philippines lies a volatile geological feature that scientists consider one of the region's most dangerous seismic threats. Recent offshore earthquakes near Ilocos Sur have been traced to the Manila Trench, an immense subduction zone capable of unleashing catastrophic seismic energy. The Philippine Institute of Volcanology and Seismology has warned that this particular segment of the trench could generate an earthquake of up to magnitude 8.4, an event that would rank among the most powerful in modern history. The concern intensified following a sequence of tremors near the town of Santa Catalina. To assess the tsunami risk such a major quake could pose, PHIVOLCS conducted simulations that divided the Manila Trench into 4 segments. Their findings revealed a sobering scenario. A massive undersea earthquake in this region could generate tsunami waves between 3 and 15 meters in height. In this modelled scenario, the first tsunami waves would strike coastal provinces including Zambales, Pangasinan, La Union, Ilocos Sur, Ilocos Norte and Cagayan within a window of 2 to 15 minutes. Palawig, Zambales could be hit in as little as 2 minutes, while Vigan, Ilocos Sur might face waves towering nearly 15 metres high, 14.7 metres to be exact. Since the early hours of December 17, PHIVOLCS has recorded 49 undersea quakes northwest of Santa Catalina. These ranged in magnitude from 1.8 to 5.0 and were linked to tectonic movement along the Manila Trench, which plunges to depths of around 5,400 meters. While the science behind these events continues to evolve, PHIVOLCS remains clear. No technology currently exists to predict the exact timing or location of earthquakes and tsunamis. Nevertheless, the agency has stressed the importance of public awareness and preparedness. Warning signs that may precede a tsunami include intense ground shaking, rapid changes in sea level, or unusual ocean sounds. Vigilance in the face of such signs could mean the difference between safety and disaster. Beneath the tranquil waters off the western coast of the Philippines lies an immense geological structure that rarely garners international attention, yet poses one of the most formidable seismic threats on the planet. The Manila Trench, a vast underwater chasm extending approximately 5.0 kilometers from Taiwan to the northern Philippines, is not as well known as the San Andreas Fault or Japan's tectonic hot zones, but scientists regard it with growing concern. This deep oceanic trench marks the collision zone between 2 massive tectonic plates, the Philippine Sea Plate and the Eurasian Plate. Unlike transform faults where tectonic plates grind past each other laterally, the Manila Trench is a classic example of a subduction zone. Here, the denser Eurasian Plate plunges beneath the Philippine Sea Plate in a slow but relentless descent, advancing at rates of up to 100 millimeters per year in some regions. This tectonic process, which has been unfolding over millions of years, plays a crucial role in recycling Earth's crust. However, it also generates extraordinary stress along the boundary where the plates become locked, a zone where energy accumulates until it is violently released in the form of earthquakes. What sets the Manila Trench apart from many other seismic zones is a disturbing silence. Despite the high rate of convergence between the plates, historical records dating back to the Spanish colonization of the Philippines in the 1560s reveal an absence of any earthquakes exceeding magnitude 7.6 along this trench. To geologists and seismologists, this lack of major seismic activity does not signal safety. It indicates a potentially catastrophic seismic gap. Over centuries, strain energy has been building without any significant release, creating conditions ripe for a devastating rupture. The analogy is often made to a stretched rubber band. The longer it is pulled without snapping, the more explosive its eventual break. Advanced monitoring technologies, including high-resolution seafloor mapping, GPS-based deformation tracking and sophisticated computational modeling, have confirmed the presence of a substantial slip deficit along sections of the Manila Trench. This term describes the difference between how far the tectonic plates should have moved based on their known rates versus how far they've actually moved. That gap represents stored energy that will inevitably be unleashed. Recent scientific estimates suggest that if these locked segments were to rupture, The resulting earthquakes could range from magnitude 8.5 to over 9.0. For comparison, the 2011 Tohoku earthquake in Japan, which unleashed a tsunami and caused the Fukushima nuclear crisis, was a magnitude 9.0 event. Each step up in magnitude represents an exponential increase in energy release. A magnitude 9.0 earthquake emits about 32 times more energy than a magnitude 8.0. In examining global seismic risks, researchers have drawn stark parallels between the Manila Trench and other infamous subduction zones such as the Sunda Trench off Sumatra. The 2004 Indian Ocean earthquake and tsunami that originated there claimed more than 230,000 lives across 14 countries. Both the Sunda and Manila subduction zones exhibit high convergence rates, long periods of seismic quiet, and the geological capacity for large-scale multi-segment ruptures. What makes earthquakes in subduction zones exceptionally catastrophic is not merely their immense magnitude, but also their capacity to generate devastating tsunamis. When a segment of the ocean floor abruptly thrusts upward during one of these seismic events, it displaces a massive volume of seawater. This sudden upheaval sends waves racing across the ocean, gaining height as they enter shallower coastal areas. For a country like the Philippines, comprised of more than 7,600 islands and densely populated coastal communities, this combination of violent ground shaking and incoming tsunami waves poses one of the gravest natural threats imaginable. The scientific challenge lies in the unpredictability of such events. While geologists and seismologists can identify zones of accumulated tectonic strain and determine where a powerful earthquake is likely to occur, pinpointing the exact timing remains beyond current capabilities. This element of uncertainty is especially troubling in the case of the Manila Trench, an underwater fault zone with the capacity for immense destruction. It is not a question of if, but when. To confront this invisible danger, scientists are employing a suite of advanced technologies. Sensitive underwater seismometers now monitor minute tremors along the trench. Across the Philippine archipelago, GPS stations track tiny shifts in the Earth's crust, silent indicators of mounting stress beneath the surface. Satellite-based remote sensing contributes a broader view, capturing the deformation of entire landmasses near the subduction zone. Each of these tools provides vital clues, helping researchers refine earthquake models and deepen their understanding of potential hazards. Equally important are geological investigations into the distant past. Coastal layers of sand and marine debris, evidence of tsunamis that struck long before written history, are yielding insights into previous megathrust events. By studying these ancient deposits, scientists can estimate how often such catastrophic earthquakes have occurred. Preliminary findings suggest the Manila Trench may produce major seismic events every few hundred to 1,000 years, and current timelines indicate that the region may be approaching another rupture cycle. This looming threat does not exist in isolation. The Manila Trench forms part of an intricate network of geological faults that slice through the Philippines, including the Philippine Fault Zone, which spans many of the nation's major islands. A large rupture in the trench could feasibly trigger movement along these interconnected systems, potentially setting off a cascade of earthquakes across multiple regions. The implications of such a sequence would be enormous. In a worst-case rupture scenario, areas near the trench could experience sustained ground motion lasting several minutes, far longer than most structures are engineered to endure. Buildings that remain stable during brief tremors often begin to fail under prolonged stress, a tragic pattern seen in past megathrust quakes. This extended shaking not only magnifies structural damage, but also increases the risk to human life and infrastructure. Ground shaking intensity would not be uniform throughout the Philippines. It would vary based on proximity to the rupture and the geological characteristics of each region. Western coastal areas of Luzon, for instance, would likely bear the brunt of the quake's energy. In these zones, seismic intensity could reach levels 9 or 10 on the modified Mercalli intensity scale, thresholds where even reinforced buildings suffer severe damage. Even though Metro Manila lies at a considerable distance from the Manila Trench, Its geographical and geological conditions make it highly vulnerable to the compounded effects of a major subduction zone earthquake. A significant portion of the city sits atop soft, sediment-filled basins that intensify seismic waves through a process known as soil amplification. Within mere minutes of a massive undersea quake, coastal communities across western Luzon could be struck by powerful tsunami waves generated by the abrupt upward shift of the sea floor. Advanced simulations show that, in a worst-case scenario, these waves could reach shores in just 15 to 30 minutes, leaving residents with only moments to flee to higher ground. Contrary to cinematic depictions of towering walls of water, tsunamis often begin as an unusual rapid surge in water level, like an unstoppable tide. Projections suggest tsunami heights could range from 3 to over 10 meters in some coastal areas, including Palawan and Mindoro. Metro Manila, with over 13 million residents and one of the highest population densities in the world, faces a uniquely perilous set of risks. This threat is magnified by an aging infrastructure. Many buildings were constructed before modern seismic safety standards were adopted. Informal settlements, home to millions, lack even basic structural engineering and are particularly prone to collapse. A cascade of failures across essential services would be almost inevitable. Power grids would likely go down instantly, leading to widespread blackouts. Water systems, heavily reliant on electricity, would cease operation. Bridges and elevated highways might collapse or become impassable, severely hindering rescue operations. In such a scenario, survival would hinge not only on emergency response, but also on individual and community preparedness. The question emerges starkly. How long could families or entire neighborhoods endure without electricity, clean water, access to food, or any form of communication, possibly for weeks or longer? Beyond the initial devastation, the situation would only grow more perilous. Landslides in mountainous areas could block escape routes, isolating entire communities. Soil liquefaction, where ground behaves temporarily like a liquid during intense shaking, could cause buildings to tilt, sink, or collapse, especially in districts built on reclaimed land or saturated soil. Fires sparked by ruptured gas lines or electrical faults could spread uncontrollably, particularly where firefighting capacity has been compromised. The broader economic fallout would be immense. The Philippines, one of Southeast Asia's fastest-growing economies, could see decades of development undone in a single day. The country's business process outsourcing, BPO sector, employing over 1 million workers and contributing around 7% of GDP, could suffer major disruptions from damaged offices and broken telecom infrastructure. Tourism, which contributed roughly 13% of pre-pandemic GDP, would almost certainly collapse in affected regions, potentially for years. The aftermath of a massive undersea earthquake in the Manila Trench would ripple far beyond the epicenter, disrupting essential sectors across the Philippines. Agricultural productivity would decline as irrigation systems break down, transportation routes are severed, and fields, especially those along the coast, become contaminated by saltwater, debris, and hazardous pollutants carried inland by tsunami waves. The financial toll would be staggering. Insurance providers would likely collapse under the weight of widespread claims, far surpassing the capacity of domestic markets. At the same time, government revenues would plummet just as emergency spending demands skyrocket, pushing public finances to the brink. Although international aid would be crucial, coordinating relief efforts in the chaos following such a disaster would pose enormous logistical challenges. Historical catastrophes serve as grim reminders of what could unfold. The 2004 Indian Ocean tsunami claimed over 230,000 lives in 14 countries and inflicted more than $10 billion in damages. Even Japan, a global leader in disaster preparedness, suffered nearly 20,000 fatalities and incurred losses exceeding $360 billion during the 2011 Tohoku earthquake and tsunami. The Philippines, with its more fragile infrastructure and limited resources, could face proportionally even more devastating impacts. Rebuilding would not be a matter of years but of decades. The 2010 Haiti earthquake, despite being much less powerful than what might occur along the Manila Trench, left entire communities in disarray for over a decade, despite the presence of international aid. A similar or stronger event in the Philippines would stretch the nation's resilience and recovery capabilities to their absolute limits. In the face of this looming threat, the focus shifts from speculation to preparedness. How can the country anticipate, endure, and rebound from a potential megaquake? The answer begins with enhancing the nation's seismic monitoring and early warning systems. Over the past decades, there have been notable advancements. The Philippine Institute of Volcanology and Seismology leads this effort, operating a network of 74 seismic stations across the archipelago. These stations continuously record ground motion, feeding critical data to central analysis hubs, where experts can determine an earthquake's location, depth, and magnitude within minutes of occurrence. Yet despite progress, the Philippines still lags behind earthquake-ready nations like Japan in terms of early warning capabilities. The limitations are not solely technological, they're rooted in the nature of earthquakes themselves. Seismic waves travel at speeds between 3 and 8 kilometers per second, leaving areas closest to the epicenter with virtually no advance notice. Only more distant communities may receive brief warnings, just seconds to drop, cover, and brace for impact. When it comes to tsunamis, the dynamic changes. These waves travel slower than seismic tremors, theoretically allowing more time to issue alerts. The Philippines has responded by installing 36 tsunami detection stations and 10 early warning systems in high-risk coastal zones. Still, challenges remain in reaching vulnerable populations in time, especially in remote or underdeveloped areas. A tsunami originating from the Manila Trench could strike the western coast of the Philippines within a mere 15 to 30 minutes, offering residents in low-lying, densely populated areas scant opportunity to evacuate. With limited access to higher ground, the urgency of such a scenario becomes a matter of life and death. The structural integrity of buildings across the nation hinges on the National Structural Code of the Philippines, initially introduced in 1972 and periodically updated to incorporate contemporary seismic standards. In theory, constructions adhering to this code should withstand moderate earthquakes with only minor damage and remain standing through major seismic events. However, in practice, this ideal is frequently undermined. The enforcement and implementation of the code remain inconsistent, hindered by insufficient resources at the local government level, corruption within the construction sector, and a shortage of trained inspectors. In Metro Manila alone, engineering assessments have revealed that thousands of buildings, including vital facilities such as schools, hospitals, and residential complexes, are perilously vulnerable to a large-scale earthquake. The country's approach to disaster response has seen considerable progress, particularly through the coordination efforts of the National Disaster Risk Reduction and Management Council. This body orchestrates a multi-tiered response strategy, engaging regional, provincial, and municipal units to facilitate both centralized planning and localized execution. Yet even with these reforms, a catastrophic event triggered by the Manila Trench could surpass the system's capacity, particularly if simultaneous crises erupt across multiple regions. Perhaps the most overlooked but essential component of earthquake preparedness is found at the community and household levels. Research consistently shows that during major disasters, the most immediate help often comes not from professional responders, but from neighbours. Communities characterised by strong social ties and basic disaster education tend to suffer fewer casualties and recover more quickly. In recognition of this, some municipalities have implemented community-based disaster risk reduction initiatives, training local emergency response teams, organising drills, and developing evacuation procedures. Cities such as Marikina and Quezon City have emerged as leaders in urban resilience, yet such programs remain sporadically applied, leaving many at-risk areas without even the most basic preparedness measures. At the household level, small but critical actions can significantly improve survival outcomes. Securing furniture to walls, knowing how to cut off utilities, maintaining a stockpile of essential supplies, establishing family communication strategies, and identifying safe zones within the home can spell the difference between safety and tragedy. Nevertheless, surveys reveal that a majority of Filipino households have yet to take even these fundamental steps despite residing in one of the world's most disaster-prone nations. The landscape of disaster preparedness is beginning to shift with the advent of emerging technologies. Remote sensing tools now offer the ability to detect subtle shifts along fault lines, while artificial intelligence is being leveraged to analyze post-quake structural damage from satellite imagery. Mobile apps can deliver real-time hazard updates and guide users to evacuation routes, and social media, for all its susceptibility to misinformation, has demonstrated its power as a tool for grassroots coordination during emergencies. These technological advances offer a glimpse into a future where preparedness is not only more effective, but also more inclusive and immediate, if integrated equitably across all sectors of society. International collaboration serves as a cornerstone of the Philippines' strategy to enhance resilience against earthquakes. Agencies such as the Japan International Cooperation Agency, JICA, and the United States Geological Survey, USGS, have been instrumental in providing critical technical expertise and advanced monitoring equipment. Financial institutions like the Asian Development Bank and the World Bank contribute essential funding for infrastructure reinforcement and post-disaster recovery efforts. Meanwhile, regional alliances such as ASEAN have developed cooperative frameworks for mutual aid in the wake of large-scale disasters. These partnerships will be indispensable in the event of a catastrophic earthquake originating from the Manila Trench, an event whose scale could easily surpass national response capacities. As the country looks toward the future, it faces the complex challenge of fostering awareness without inciting fear. Public education about the dangers posed by the Manila Trench is vital to encourage proactive preparedness, yet this must be done with sensitivity to avoid triggering panic or fatalism. Compounding the difficulty is the persistent tension between economic development and disaster risk reduction, both of which vie for limited governmental resources. The retrofitting of vulnerable infrastructure, though critically important, is prohibitively expensive. Nevertheless, failure to address these structural weaknesses could lead to catastrophic human loss in the event of a major quake. A realistic and sustainable approach is likely to take the form of phased, pragmatic progress, prioritizing the retrofitting of essential facilities such as hospitals, schools, and emergency response centers can create a foundation for broader resilience. Over time, this can expand into more comprehensive programs that include residential and commercial structures. Simultaneously, there must be continuous investment in the advancement of early warning systems, which could provide crucial seconds or minutes to act during a seismic event. Yet no amount of technology or policy can substitute for a deeply ingrained culture of preparedness. True resilience emerges when individuals, communities, businesses, and all levels of government understand and embrace their respective roles in reducing risk and enhancing capacity. While the Manila Trench represents one of the nation's most formidable natural hazards, history has demonstrated that societies which unite, plan, and adapt can not only survive disaster, but also rebuild stronger in its aftermath. The objective is not to eliminate risk, an unattainable goal, but to reduce vulnerability, strengthen capabilities, and cultivate the social and institutional resilience required to face future challenges. In doing so, the Philippines can transform a looming threat into a powerful catalyst for national strength and unity. If you found this deep dive insightful, don't forget to like, share, and subscribe for more explorations into the powerful forces shaping our world. Stay informed, stay prepared, and above all, stay curious.